Okay, good morning. We'll start. Okay, so the topic of today will be computer vision. So it should be like a more lightweight, I would say, lecture today. It will be mostly about describing architectures to solve tasks, which are more complicated than maybe what you are used to. I'll come to that. But other than that, it will be a basic description of architectures. Okay, so today we'll talk about 3 tasks for computer vision. The first one is classification, which you should be familiar with. You are given an image, and then you want to classify the content of this image. Second, we'll talk about object detection, which is given an image to detect various kinds of objects or things or people or animals or whatever. And so it means that you need to understand the content of subregions of an image. And finally, we'll talk about segmentation, which is the task of dividing or classifying the pixels with a class. Okay? So in these slides, you see 4 different computer vision tasks. The first one that you see there is about classification and localization. So you all recognize that, okay, there are sheep in the image, so it's classified as sheep. But if you want also to solve the localization task, basically the task is, now that you know there is a sheep or multiple sheep in the image, where are they in the image? Okay. Second is object detection, which is very close to the previous one, except that you don't know in advance if there is any sheep. Okay. So in this case, you have to detect all instances of sheep, and so you recognize. So basically, the task is a regression task for which you have to predict or guess or estimate the boundaries of each object or each animal, each sheep. In this case, you have 3 of them, so you would need to make 3 predictions. The next one is segmentation, and there are again different kinds of segmentation. The first one is what we call semantic segmentation, in which you basically treat each pixels individually, and you want to classify each of them with a class. So, for example, all this part of the image should be classified as road, all this part in green as grass, and everything in between as sheep. Okay? And then the variation of semantic segmentation that we can consider is instance segmentation, in which not only we want to segment the entire image, but we also want to detect each instance. And so in this case, we would still classify the pixels similarly for the background, so the road and the grass, but when it comes to the sheep, we want also to detect that there are 3 instances of this object, or of this class. Okay? And what we'll see today is that if you want to solve these problems, you will need a dedicated neural network architecture to solve it. Okay? That's what we'll try to answer today. All right. Okay, so a brief recap on classification. So we have seen last week that we can build neural networks with convolutional layers and pooling layers, and we can compose them into what we called convolutional neural networks, or CNNs or convnets. And if you say that the output layer of this convnet is made, for example, of a softmax activation function producing probability estimates, then you have everything that you need to classify images. Okay? So this is what we saw last week. These CNNs are just combinations, compositions of convolution, pooling, and fully connected layers, and everything you need at the output. Okay? So these neural networks, they are still state-of-the-art when it comes to processing what we call spatially structured data. So basically when you have a signal, like an image, like sound or text, where you know that there is a structure, a geometric structure in the signal. Okay? And so that means that, yes, for example, you could use a CNN also to classify sentences. Okay? Or yes, you could use a CNN to classify speech. Okay? An image is like just a 2D version of a one-dimensional signal. Okay? But you could have convolutions with kernels just in one dimension and apply the same kind of architecture. Okay? So CNNs, I've just said that they achieve state-of-the-art results, but we'll see nonetheless next week that these days you have better architecture, so they used to be state-of-the-art, strictly speaking. They are more or less in competition, I would say, with other architectures, like transformer neural networks, which we'll see next week, but still, every time you have a machine learning problem in which you have to process a signal of this kind, then using a CNN as a baseline is certainly a very good idea. Okay? Okay, so how do we make a CNN a classifier? Well, as I said, the only thing you need to do is to take any CNN architecture and then you modify the output layer. And so what you need is a softmax activation function which will produce a vector h of probability estimates, so a vector of dimension c, where c is the number of classes you want to predict. And the loss then that you would use is the same loss as for any classification problem. It would be the cross-entropy loss. Okay, and then you are good to go with everything we have seen. Well, in practice, you will certainly, if you just do that, you will face issues, or you will produce results, but maybe they may not be that strong. And really, the main bottleneck when it comes to training CNN, or basically training any kind of neural network actually, is the lack of data. Okay? So if you have one thing to do when you will work on an actual project, or when you will work on your project, you will gain the most by just collecting more data. You could spend weeks or months just tuning the architectures and trying everything. But really what would pay the most is just to collect more data. Okay? So that's a big lesson you should remember. However, collecting more data is usually expensive and laborious. So if you're given a data set for your project, you may not have the opportunity to collect yourself new images or new training pairs. So that's something maybe you can't even do. But if you can do it, usually that will be a long process, and maybe you want to avoid that. But if you can, really, you should do it. So you could say, okay, maybe if I want to increase the size of my training set, I could maybe create new data artificially. Okay, and this is something we'll see in the last lectures. There are actually ways to generate data. The issue is that if you use artificial data, you will not be sampling from the true distribution. So you will be using instead synthetic data, which may have artifacts, defaults, defects. And if you train then on that, okay, maybe you will get good results on this artificially generated data, but there is no guarantee that it would work quite well on the true data distribution. An alternative to these two things is what we call data augmentation, which is a very, very simple idea, which is to say, maybe depending on the problem, there are quick variations of my data that I can produce, which would still be relevant for the task. And specifically, for example, for the case of images, if you are interested in classifying images or detecting objects in images, and you are given just a finite training set, let's say with 1,000 input-output pairs, then something that you could do, for example, to train a better classifier or better object detector would be to augment the data by just applying image transformations to the input images. And so, for example, if you translate the images, it's still the same content, and you still expect that your classifier or your neural network perform well on these translated images. But if you don't show these translated images to the neural network, there is actually no guarantee that it would work quite well. So it's actually often very beneficial to do that explicitly yourself by just generating these random transformations. And so you see a few of them there on the slide. You could have transformations that are based on the geometry of the image. You could, for example, consider rotations, shearing, flipping vertically or horizontally. You could also consider cropping, padding, changing the perspective, making elastic transformations, whatever you think is relevant. You could also consider changes on the colors of the images, like you sharpen the image, you brighten the image, you change the contrast, maybe you invert the colors, if that makes sense. You could also consider different kinds of noise, like Gaussian blurs, additive Gaussian noise, random translations, horizontal translations, random vertical translation, and so on and so forth. Or you could also start adding other kind of noise, like clouds, fog, and so on and so forth. Okay? And you may think that, okay, this is not really clever, and I would agree with you, this is not very clever, but when you do that, and this is a plot showing the same architecture, the same neural network trained on this kind of images, coming from the CIFAR10 dataset. If you just train a vanilla CNN, you would get the result, the validation accuracy that you see there in blue. And by just considering this random transformation at training time, okay, then in this case you could gain more than 8% in accuracy without changing anything to the architecture. Okay, so every time you have a basically computer vision task, it almost never hurts to just consider also random augmentations of the data. It will, it will improve certainly the results. Okay, one other thing you can do is to say, okay, maybe my dataset is too small, and there is no way I could train a very strong CNN on this small dataset. What if instead I start training from another neural network that has already been trained, but on something else, on some other task? Okay, so that's what we call pre-trained models, and there are many of them that you can find on the internet. You can download them, even some of them directly through PyTorch or other APIs. And basically, this neural network, they've been trained already on very large datasets, like ImageNet dataset or other datasets. They are usually quite large. They've been trained for days or weeks. Okay, but you may think, okay, there is, if this, for example, if you take a neural network trained on ImageNet dataset, it can classify thousands of, it can classify an image among 1,000 categories. But maybe you want to do something else than, of course, producing these same categories. So the idea is just to say, well, you will take this pre-trained neural network, you will remove the last layers of this neural network, and you will consider the remaining part as some kind of feature extractor. Okay? And then you pass your images from your small dataset through this feature extractor that produce a new representation of the image, and then you only train a few additional layers on these features. And usually that's very efficient. Okay? And so this is what we call transfer learning. So you take a pre-trained neural network, you remove the last layers, and then you treat the rest of the network as a fixed feature extractor. Then you train a model from these features on a new task, okay? And what you will often notice is that you will get results that are better than if you had trained directly on your training set. Okay? And the reason is that the features that you learn on one vision task, they are very often transferable to other tasks. Okay? And you only need a few tuning steps to make sense of these features for your new task. Okay? And so this is an illustration which was done a while ago in 2018 by someone from the lab at Montefiore. And he wanted to process this kind of biological images, but he had only access to a few of them, maybe a few hundreds of them. And so what he did was to take a pre-trained neural network, trained on ImageNet dataset, so where this network has been trained to recognize cats, dogs, boats, buildings, something very far from these biomedical images of cells or tissues. But you just apply this recipe, you take the pre-trained neural network, you remove the last layers, and then you add a very shallow model at the end, like a very shallow neural network, or you could even plug a traditional machine learning model, like an SVM or something like this, and you train it, and what you get are, in this case, very good results. At least results that are better than if you are trained only on the small dataset. So this is what we call transfer learning. There is an alternative to that which we call fine-tuning, which is basically the same idea, except that instead of considering the feature structure as something which is frozen, okay, which for something that you don't train anymore, you fine-tune also the weights, the parameters of this neural network. Okay, so in this case, you would take a pre-trained neural network, as before, you would remove the output layer, you would add something else, a new output layer or a new shallow model. And in the case of transfer learning, the layers before were considered frozen. You would not update them when running your optimization loop. In fine-tuning, you say that, okay, you can also keep improving these layers, these parameters, and train the whole thing. Okay? So that's a bit more expensive, because that means possibly this neural network is very large, and so you need resources to do that, but if you can, usually you will get better results. Okay, and this is another plot showing this, where you see results for a few neural networks, ResNet, Inception V3, VGG19, and others, and everything in dashed. So the one above are all trained, or basically they all come pre-trained, and then you fine-tune them on a new domain. In this case, it's a paper trying to process paintings, so something also very far from natural images. But what you see is that all the pre-trained network, when you fine-tune them on this new domain, they achieve better results than, for example, the one in orange, which was trained directly from scratch on the dataset of paintings. And again, in this case, the improvement can be quite significant. Okay, so this is something that you should also realize when it comes to deep learning. Now, more and more, or less and less, I would say, we are training neural networks from scratch. Instead, we start from pre-trained neural networks. Maybe we change or remove a few layers, but then we compose them to build bigger architectures and to bootstrap basically the optimization, the train. Okay? Questions on this? Yes?
When you say fine-tuning, you just mean training a neural network that has already been trained?
Yes. You continue the training of this neural network. Exactly. All right. So classification is, should be quite easy. Now the next task that we will consider today is object detection. So let's say you have an image, which can be quite big, and you want to detect objects or things in this image. Okay? So let's say maybe you want to detect cats. And maybe there is another one there. How do you do that? What would you do? So I give you an image, and basically what you want to produce as an, given this image, what you would like to produce as an output is the localization of this cat as a bounding box, and the localization of this other cat as this bounding box. And maybe there are several things that you would want to recognize. Maybe there are dogs also. How can I do that? Okay, something like this. And the dogs, of course, they are not cats, so you should recognize that another kind of entity, but you would also want to locate them. So how would you solve this problem? Yeah. Yeah, you.
Is there cats or dogs in the whole image? Yes. Let's have some region of interest. Is there some cats or dogs in this subset? Yes. And by going so, we can know where a property is and where it is not.
So you would start by just processing the entire image.
And after looking some subparts of this image.
Okay, but what do you think will happen when you feed this entire image? To what would you feed this image, by the way? To a neural network, I suppose, something like this. And what would be the goal of this neural network?
To find if there is a cat or a dog in the image.
Okay, but how do you state that? Yeah.
You can use classification neural network.
Okay, you could say, I know how to classify images, so I could just feed this entire image to this classifier. And in this case, what should be the expected outcome?
To classify cats and dogs.
But maybe there is no, maybe in the image you don't have any cat or dog also. Yes?
We cut the picture in several small parts.
Uh-huh.
Each of the parts we feed them individually to a neural network. Those binary classification, yes, there is what we search, no, there is not what we search.
Mhm.
Then we can see this part of the image, there is what we search, and this part, there is nothing.
Okay, so you would say you divide the image into subregions, and how would you do this division? Like you say you have a grid. I don't know.
First, we can make a grid, but we have to not, so for example, cut the
Mhm.
image.
So you could say you have a grid.
Here we are cutting the sum of the image in individual cells.
Yeah.
So we have to shift kernel-like input.
Okay, so you would have a first maybe region, and then you would shift maybe this other region like this. Like this?
Yes.
Okay. And then you would go all the way, and then I suppose you would shift then down, and you would consider the next image, and so on and so forth. Okay? What if you have very small cats? Or very big ones?
We could first try with large canals, and then when we detect that there is something in the large canal, we try to reduce it, and we try in the smaller.
Mm-hmm. So you would have a classifier for each class also. So if you have 10 different things that you want to detect, you would have 10 models that you would run on this.
If you want to recognize what is in the image, we would have a classic classifier with you can recognize several things, but
Mhm.
here you ask just to find cats. So,
Or dogs.
so that's why I said a binary classification.
Okay. But that's a good idea, and that's one of the first kind of object detector which was implemented but a long time ago. And the idea is really that you run a window over the entire image, and then for each location of the window, you run your classifier, and then it predicts if there is, for example, a cow, in this case, in the content of the window. And you do that also for, so you repeat that for all the locations, but also for different scales of the image. Okay, because you may have small cows, at least in the image, and larger cows in the image. Okay? So you could do that, but the big issue of this is that it's very computationally expensive, because the performance or the number of operations you would do, or the number of forward passes you would need to perform, is directly proportional to the number of locations times the number of scales that you would consider. Okay? That's very expensive. So how could we reduce the complexity of this approach? So the main problem really is that if we do that, we will have many locations that we have to consider. And basically one of the issue will be to decide on the stride that we use in between two locations. If the stride is large, we will reduce the computations, but then we risk dividing an object in between two windows. If the stride is small, and the smallest it can be would be 1, then we would not have this risk, but then the complexity will blow up. Yes?
Maybe I'm not sure, but can check like for region that haven't that has not big changes. For example, if there is the sky in the image, there is no change in color and luminosity, so you can remove this part from the search because if you're looking for objects.
Yeah, but then you do something which is very specific to the problem you are trying to solve. Which could be a good idea sometimes, but in this case, yeah, I don't think that's efficient. So how could we improve the complexity of this algorithm? Yeah.
Start from the big image, decrease its size, unless we don't detect what the number is anymore, or there is a change in what's detected.
What do you mean?
If, for example, we use this image,
Yeah.
and we have the whole image,
Yeah.
and then instead of looking at,
So you start from a big window.
yes, we start
Yeah.
from a big window and we decrease it, and at some point there is, for example, the dog that will disappear, and we see that yes, the dog has to be in. It gives a clue where the dog is.
So there are a few issues with that. The first one is that your classifier neural network will not be scale invariant. If you take an image, you zoom in and feed that zoomed in image to a neural network, you will not get the same result as with the original image or when you zoom out. So you cannot rely on that. And then there is the second issue is how do you make the window smaller, in which direction? And how do you deal with the fact that there will be several objects that you want to detect, not only one? And you don't know in advance how many of them there are. So what could we do? So the trick is to make the neural network do more than just classifying. So one thing we could do is to use a very coarse grid where we would have big windows and a big stride, I don't know, like this. And we would have several of them at different scales, but we would keep this grid very coarse, okay, with a very big stride, okay? And what we'll ask the network to do is not only to classify the content, but also to locate the content. And by that, I mean that the neural network should produce, so you would have the neural network taking as input one of these windows and producing first a class, so vector h of size, the number of class, and also the position of this thing. Okay? And what do you need to specify the position? You need to basically have a way to encode this rectangle. Okay? Or and what you need, so there are several ways to do that, but one way is to produce the coordinates of this corner, okay, I, j, together with the width and the height. And if you have these four numbers, then you have this rectangle. Okay? So now you would also have four additional output elements, which would correspond to the coordinate. And so then the trick is to say, okay, we are using a coarser image because that will be more efficient. I will have fewer computations to do. But then to compensate for these coarser operations, I will also ask the network to locate within this window the content that I'm looking for. Okay, and this, if you do that, then you get first architecture, which we call overfit, which no one is using anymore, but I think it's still interesting to understand. It was proposed in 2013, so ages ago, when it comes to deep learning. But it's really just implementing that. You have an input image, or the window of an input image, that goes through a CNN, and then you have two heads, you have two outputs. The first one corresponds to the classification of the content of the image. In this case, for example, among 1,000 categories. And then finally, you have these four additional numbers, which correspond to the coordinates of the object. And so then the idea is similar as before for each location and scale that you have defined beforehand from a coarse grid. So you would have, for example, the grid which you see there on the left. Okay. For each of these windows, then you pass the corresponding content of the image to the architecture, to the neural network. And then the neural network would produce for each of them a class together with the coordinates of the rectangle. Okay. Now, what you realize if you apply this strategy is that you are left with many, many, many predictions. Yeah.
But how would the classifier work if, for example, the cat and the dog are like just close to each other, such that they are both in the same window?
Yeah. Yeah. That's a good question. So if you have a dog there, just there. Sorry, like this. And you would want to produce this. You need to have, in this case, a grid which is coarse but still fine-grained enough, such that there will be a window for which you only see the cat mostly, and another for which you only see the dog mostly. Okay, so it's true that this algorithm works under the assumption that there is at most one element, one object in the window. Okay, but then I was saying, okay, if you apply this, you will have as many predictions as the number of windows that you consider in your grid. So how do you basically clean these predictions? Which ones should you select as the final output of your system? So the idea is to use a post-processing algorithm to merge all the bounding boxes which correspond to the same thing. Okay, and the algorithm which is used very often in computer vision is what is known as non-maximum suppression, and this will take a list of bounding box and only keep the one of you wants. Okay, and so the idea is to start with all these boxes. Each, by the way, come with a confidence score. Okay. Then you sort all the boxes with a confidence score. The confidence score, for example, could be the classification probability associated to the box. You sort all these boxes from the most confident to the least confident. You select the box with the highest confidence. You add it to your list of final predictions. And then what you do is that you calculate the overlap between this box and all the others that remain maybe to be included, and you discard all the boxes that are overlapping sufficiently with the box that you have kept. Okay? And then you repeat that, simply. So for example, if you go like this, maybe there would be, among all these predictions of the Burr, you would sort all these boxes, you would keep the one for which your classifier is the most confident, and then you just compute the overlap between this rectangle and all the other rectangles, and all the rectangles which are overlapping enough, or which are really overlapping with the one that you've selected, you remove from the list of boxes. Okay? Then you are left with some rectangles, which again you keep sorted, you take the next one, and that produces your next prediction, which you compare with all the other that remains. You remove all the ones which are overlapping with this second rectangle, and so on and so forth. Okay? Okay, so that works, but this architecture comes with several drawbacks. So it's a disjoint system, so it has two heads with their respective losses. That's something really that you will see we won't really solve. However, what it does is that it optimizes for localization rather than detection. So it assumes that there is something already in the window, but it may be that there is nothing. And more importantly, one of the biggest drawback of this architecture is that it's processing these windows in isolation, and it does not know about the context around these windows. But if I'm drawing, for example, if you have a training set of images of natural images, and maybe I have something like this, what do you think I've drawn there? Birds. Why? Yeah, they are in the top. What if I had done something like this instead? Okay, but it looks like birds, right? At least in my drawings. But you know how to differentiate the two because you use the context of the entire image. Okay, but if you apply this overfit architecture, it does not know about the context because you would just take a crop of the image, and the classifier processing this crop does not know where the crop was taken from and what's around it. Okay, so the fix for that was a breakthrough architecture, YOLO, for you only look once. It was proposed 10 years ago, but it's still something that we use, or at least improvements of this architecture. And the idea is to instead of processing the image, the windows one after the other, we just take the entire image and produce at once all the windows. Okay? So you will not have a neural network just producing one output, or maybe two outputs, a vector of classes and a position. You will have many of them produced by the same neural network at once. Okay? And so the idea is quite simple. You take an image and you divide it into a grid, in this case an S by S grid. Okay? And then you say that your neural network should produce one of these pairs or several of these pairs of predictions for each cell in this grid. Okay? So for each of the cells that you see there in black, you will design the architecture to predict B bounding boxes, so the coordinates of B rectangles, confidence scores for these boxes, so how confident are you about whether or not there is something that you're looking for in this box, regardless of what that is, together with the class probabilities that you associate with your objects. Okay? So that means we'll have a single neural network that makes at once S by S by 5B plus C predictions. Okay? Why 5B? Because we have 4 numbers to produce for the coordinates of the rectangles plus the confidence score. Okay? And so the architecture of YOLO, the first version was something like this, which is very similar to what we have seen last week when we covered a few of the main CNN architectures. This one is actually close to the VGD architecture. So it starts by the image that you see there on the left, and then goes through a convolutional backbone where you see convolutional layers and max pooling layers. The nonlinear activation functions are not shown, but they are also nonlinear activation functions, of course. And you see that as the image passes through the network, it becomes smaller because of the pooling layers, but at the same time we increase the number of channels to represent these images. And what's different is the output layer. So up to there you still have a feature map produced by the convolutional backbone. And there everything is flattened into a big vector, okay, but then reorganized into a 7 by 7 grid times 30 channels. So this is the case when you have S equal to 7. So you have these two dimensions correspond to the dimensions of the output grid, so S by S. We have 20 classes, and I said per cell we would need 5B plus C elements. Okay, so if B is equal to 2, we have B times 5, 10, plus 20, 30, and you get 30. Okay? So that means now this neural network will take the entire image, divide the image into this S by S grid, and for each of them, for each of the cell, will produce basically up to 2 rectangles, in this case for B equal to. And for each, you have the location of the rectangle, which, by the way, may not be necessarily inside a cell. What you consider in this case is that the center of the object is within the cell. Okay, but the rectangle that you predict could be beyond the cell. You predict for each of the rectangle also a confidence score, and then finally a vector of probability classes. Okay? What is different from before is that this architecture, because it processes everything at once, is able to take into account the context, the global context of the image to make its predictions, and not only what's inside the crop. There is no crop, which makes it really more efficient. Okay. But then there is the question, how do you train this kind of neural network? What loss function do you use if you have to produce that many outputs? So you can't just say, I will minimize the cross-entropy loss, because that makes no sense when it comes to the coordinates that you have to predict, for example. So how would you train this neural network? And of course, you may have a data set of images for which you know objects and their locations. Okay, so to introduce the loss, I need to introduce a few notations. So the first one, the first assumption will be that in each of these S by S L, each of the S by S cells will contain at most the center of a single object, as I said. And then for every image, cell index I going from 1 to S by S, we just enumerate the cells. Okay. Each of the B predicted boxes from 1 to B. Okay, and I will use the J letter to denote that. And then finally, for each class index C from 1 to C, let's define all these elements. So I will say that 1 is equal to 1 is true if there is an object in cell I and 0 otherwise. That's something you can get directly from your training set, training time. Okay. So if really, for example, in your training set, there was an object there for this cell, okay, then this element is set to 1. And if there was nothing, for example, there, it's set to 0. Then we'll have that this variable 1 object of ij is equal to 1 if there is indeed an object in this cell I. And among the predicted boxes for this cell, the box J is the one which is fitting the most with the object. Okay? Otherwise, it's set to 0. Then you have PIC, which we set to 1 if there is an object of class C in cell I and 0 otherwise. That's something we get from the training set. Then we have the coordinates, which are something also that you get from the training set. And finally, Cij, which is the overlap measured in terms of the intersection over union between the predicted box and the ground truth target. Okay, so this IOU thing so let's say this is the ground truth box that you would have to predict, and this is what your system predicts. Okay, what we call the intersection over union is simply the ratio between this area, the intersection, over the union of the two boxes, which would cover L. Okay, and that would be U. Okay? So, if this is B2 and B1, we have B1, B2 over. Okay? And so we use this, so you get a number which is close to 1 or equal to 1 when you have a perfect prediction, and which gets closer and closer to 0 when there is no overlap. Okay, and when they are completely disjoint, then this is equal to 0. Okay, and we'll use that as a score to characterize the quality of the prediction. Okay, once we have defined all of these elements, we can finally define the loss to train this YOLO architecture. And this is the loss which was proposed in the original paper. You see that it's made of several elements. The first term corresponds to the simply to the squared error of the coordinates, the predicted coordinates with respect to the ground truth coordinates. Okay, so you see that you iterate over all cells, you iterate over all rectangles for each cell, but you only select, so this is equal to 1, only if indeed in the training set there was an object at this cell I, and you only look at the predictions which is most fitting. So many of these terms will be equal to 0. But for the one which is the closest, then you want to improve it. Then yeah, you have the same for the confidence score. So you compare the confidence score produced by the neural network, C at ij, to the IOU that you've computed before. You also want to, for all the, in this case, for all the elements for which there is nothing, you want the confidence score to be as low as possible, the closest to 0, because there you should not predict anything. So if you say if your network say it's confident there is something, but actually there is nothing, you should penalize the network for making these predictions. And this is what you get by this term. And finally, you simply have a loss for the classifier. Okay? So there are a few weird things about this loss. The first one is that it's using a square error to classify to quantify the quality of the of this vector of probability estimates. You could have used, and maybe you should have used, instead the cross-entropy loss, but they stick to that. You also see that when it comes to the coordinates, you use the squared error for the corners, or in this case, rather the center of the object. But then you use the squared between the square root of the dimensions. And the reason they do that is that if we're not using the square root, then you would be, in a sense, favoring more the larger objects over the smaller ones. What is important is that very quickly you should realize that when it comes to designing and then training one of this network, you have to make many engineering decisions. And my point is just to illustrate that when you will have to do that in practice, certainly we will be faced with these things. You will not have just a simple neural network to classify something that we know how to do, but maybe, and certainly you will want to do something a bit more involved, and very quickly it becomes a bit messy like that. In addition to the loss itself, to make it work, they had also to make a few other design decisions. So in this case, they started from a pre-trained neural networks for the first 20 layers. They used a resolution of the image of 400 by 400. They use leaky ReLU for all layers. They use dropouts, that's something we'll see later on. They normalize the parameters of the bounding boxes. They use a quadratic loss, not only for the bounding box coordinates, that's something we've seen, but also for the confidence and the class scores, which is a bit more surprising. As I said already, they use the weights of large bounding boxes by using the square roots of the dimensions. They also reduce the importance of the empty cells, and so on and so forth. They also use data augmentation. That's something I've discussed already. But you see that, okay, it's not just it's not just writing the architecture of the neural network. after that, there are still many things to be decided, and that's something you will have to do in your project. But still, if you do all these things, eventually you can produce satisfactory results. So this is a video of predictions of this architecture, the YOLO architecture, on a scene in New York. So you see that we have several objects, in this case cars, traffic lights, pedestrians, bicycles, and maybe other things. And the network is able to detect them. So what do you see? What comments or could we make about the quality of the results?
It seems good, but sometimes it confonds car and truck.
Okay, yeah. So there may be classes that are difficult to distinguish from one to the other. What else? Yeah.
Sometimes it loses the tracking of a car or person during one frame.
Okay, and why do you think that happens? Yeah.
Because they split the video into the frames and
Yeah.
they use the neural network of each frame where you should have trained the neural network in videos.
Exactly. So the flickering that you see is a result of the fact that this YOLO architecture is applied frame by frame, and actually there is no tracking. Okay, the neural network does not see the video. But indeed, if we had instead designed yet another neural network, which would be more complicated than this one, which is able to track to process videos, then we would have less of this flickering effect. But other than that, you also see that it manages to detect big objects, very smaller objects. It's not making crazy predictions for the sky, okay, because it knows that, or it has learned that from the context. So it's not too bad. Okay, what time is it? Okay, maybe I can go quickly over that and then we'll take a break. So there is an alternative to this YOLO architecture. So the nice thing about YOLO architecture is that it's doing just a single forward pass through the network. You take the image and then in a single forward pass you get all the predictions. Okay, but one issue with that is that you are limited by the quality, in a sense, of the grid that you assume initially. And maybe it would have been better to do it in two steps. First, by more or less trying to identify interesting regions where you think there is something to be detected, and then only then you do the detection inside. So this is the strategy which is implemented by what we call region-based CNNs. And so instead of having this huge predefined set of box proposals, we will use on region proposals, which are produced by another algorithm or by another neural network. These regions will first be extracted from the image, so you will have a first pass through a first algorithm or a first pass through a first neural network. Then you get just a few interesting promising proposals, a few regions, and then you apply a second neural network, so you have a second pass to detect the content or to detect the object in these interesting regions. So the first architecture which was based on this idea was RCNN, which is also quite old. I don't remember from when it was, but more than 10 years ago. And the idea is to use an algorithm to select interesting regions. In this case, they use selective search. And then once they detected interesting region, they use a pre-trained CNN, which they applied on each of these regions. This CNN was just used to produce features, like a feature structure. And then from these features, a prediction for a class was produced by another model, in this case, the shallow support vector machines. And so what you have is what you have there, for example, in this at the bottom of the slide. You have first an image. This image is passed to a selective search algorithm. This algorithm produces two regions, this rectangle and this other rectangle. And then these two rectangles are each processed independently by the second part of the architecture, in this case, first a CNN that produce features that are fed to an SVM and finally produce a category and coordinates for a box. Okay, so that's interesting, but basically we delegate a lot of the work to an auxiliary algorithm, this selective search algorithm. And of course, if the proposal produced by these algorithms are not very strong, you will not get good results. So I will skip that, it's not important. But the idea in the next version, fast RCNN, is to say, okay, instead of no, it's still based on this same selective search. Okay, let's do it in two steps. So the quality of this algorithm is bound to the quality of the selective search algorithm. Fine, let's keep it for now. But second, the complexity of this approach will grow with the number of proposals that are produced by the selective search algorithm. So if your selective search algorithm produces many proposals, that will, the time complexity will deteriorate because you will have to make as many forward passes as proposals were produced. So you can do something similar as in YOLO, where you have an image, and for this entire image, you have a big CNN which will process the image at once to produce features. And then you combine these features, which are still aware of the locations of the things that are represented in the image, together with the selective search algorithms. And the idea will be to say, in this volume of features that has been computed by the CNN, you only extract the parts that do look interesting as produced are estimated by the selective search algorithm. And within this volume, then you continue and produce a category and a bounding box. Okay? So that the computationally intensive part of just processing the image through big CNN, you only do it once, and then you look at subregions of this volume of features. Okay? So that's what we call fast RCNN. And then the final improvement is faster RCNN, where basically you say you drop the selective search algorithm and you will use another neural network to produce these proposals. And so again, you have an initial backbone, a CNN, which produce features. These features are then passed to this region proposal network, which is itself a CNN. Okay, and we'll produce also something close to these rectangles, but not yet, and we just propose the coordinates of regions to look into. Again, this can produce many predictions, many regions. You clean this list using non-maximum suppression, exactly as before. That produces just a small list of regions. And then finally, you do the same as before. For each of the region, you select the subvolume in the features produced by the backbone, and you pass that to the next part, which is about producing the exact boundary of the object together with its class. And now if you compare this to the first algorithm, or the first approach. So this is what we had before with YOLO. There are two other variations of that. And the last one which we have seen is this one, faster RCNN, where we are also solving the same problem. But if you compare the quality of these two, what could you say? So which one do you prefer, basically?
The first one.
This one? Okay, why?
We do not more lose the tracking of objects in frame
Mm-hmm.
rather than CD. And it's more smooth.
Mm-hmm.
In the first one, when we have a pedestrian, it doesn't detect the bag or something else that for this purpose was not useful. For the cars, we don't mind knowing that the person has a bag or not.
Mm-hmm. Okay, yeah. But so usually what should happen is that when you have this two-pass strategy, the quality should improve because basically you have more compute to arrive to your final detections. But, and that's something maybe you don't see, yeah, it's not reported. But also because it's doing the predictions in two steps, the frame rate that you can achieve will be lower. Okay, so you will be able to make fewer predictions per second because you need two passes through your network. While this one is faster because there is only one pass through the network. So you achieve a higher frame rate, but you lose in quality in this case. Okay, just a few takeaways and then we'll take a break for this first part. So we have seen two strategies for object detection, what we call one-stage detector, like YOLO, but there are others like SSD, RetinaNet, and whatever. They are fast for inference, but usually they will not achieve the most accurate predictions. And on the other hand, you have these two-stage detectors, like fast RCNN, faster RCNN, and a few others, which I've not talked about. They are slower, but usually they will produce more accurate predictions. Okay? And whatever you pick, when you look in the inside of these architectures, you will see that it's not nice. There are many engineering decisions. Everything is not always very principled, but usually in this community, as long as it works, it's okay. Questions? Comments? Okay. Then let's take a break and we'll resume at 10. Oui.
There's many outputs, as we have pixels time classes, and for each pixel, the confidence intervals.
Yeah, we could do that. So you would have, in a sense, a very big classifier which would produce as many outputs as you have pixels, and that for each of them would produce a big vector of probability estimates. And okay? And so that means, let's say we would start from some image like this, which is a H by W by 3 image. It would go into something that is left to be defined and would produce a map, which is itself a tensor of dimension H times W, but where we would have as many channels as we have classes. Okay? Now, how do we go from this guy to this guy? So, what architectures could we use to solve this task? Mm-hmm.
precise, but will in a coarse way find if there is someone or not.
Mhm.
After just typical architecture that the goal is to expand the output dimension.
And how do you expand? So have we seen a kind of layer that we can use to expand, so to go from to expand the dimension of the input? So you are correct. We could have a first half where we have a CNN, which will produce features about this image, and certainly these features will be relevant to solve the task. But with a typical CNN, the tensor, which is processed from one layer to the other, would reduce in spatial dimension because of the pooling layers. So how do we recover the original spatial dimensions then? So maybe the first strategy could be we don't do any pooling. If we don't do any pooling, we'll only have convolution, nonlinear activations, and provided that we do the convolutions with padding, we could conserve the spatial dimensions of the input all the way up to the output. Okay? So we could do that, and we would have something like this. And hopefully that would produce a tensor of the correct shape from which we could extract the segmentation map. The issue is that if we do that, this neural network in between certainly will be quite inefficient because it's the receptive field of the convolutions inside would grow only linearly with the number of convolutions. So if we need to make big mask or to take into account large parts of the image, we will need to have a very deep neural network in order for these neurons to have a receptive field which is big enough to cover the regions that we want to segment, for example. Okay? So that's a big issue. Yeah.
Maybe we should take the idea of a convolutional neural network and do it in reverse.
Okay, what do you mean doing it in reverse?
When you do a convolution, you lose dimension with each layer, you get smaller and smaller layers, and we should take the same thing and reverse each arrow.
Yeah, but mathematically, how would that work? Yes.
Maybe something that copy-paste one value in a square of 4x4, it's
Uh-huh.
2 dimension, and then that can be, and when the dimension will be h times wy, that can be another gloss with the initial picture to see if it's close or not to the original one.
Yeah, so the two ideas are quite good actually, and we'll see the two of them. So you could actually do the inverse or the opposite of a convolution. That's what we call a transpose convolution, and you can do that to increase the output dimension. Or you could use an upscaling algorithm, like bilinear or something like this, like what you said when you copy the pixels, to upscale the spatial dimensions, and then you follow that with regular layers. So that's what we see. But basically, that means we'll have something like this, which we have guessed correctly. We'll architecture the neural network in two parts. In the first half, we'll have a regular CNN, which will downsample from one layer to the other, or from one block to the other, the spatial dimension to reduce them. But at the same time, we'll typically increase the number of channels. And then, at the middle, maybe we'll add some neural network to process this middle part. But eventually, we'll follow that with the second half of the architecture, which will be responsible for upsampling, increasing back the dimension, the spatial dimensions, back to the dimension of the original image. Okay? The question that we may ask ourselves then is, but how do we upsample? How do we go from, for example, here, an image which is reduced by a factor of 4 in the 2 dimensions, back to a larger image, which with a factor of 2 only in reduction of the 8 and the width. And so we could say, we could do the transpose convolution or the upsampling. So let's see further transpose convolution. So transpose convolution is something that should be quite easy to understand. You take a regular convolution for which we've defined a forward path. Last time we defined it how we define the forward path. And I've also told you, actually this convolution can be rewritten as a matrix times a vector operation. Okay? From which then you can guess the backward path. Okay? Now, transpose convolution is the same as convolution, but you swap the forward and the backward passes. So you use as an implementation for the forward pass of the transpose convolution, use the backward pass of the convolution, and for the backward of the transpose, use the forward of the regular convolution. Okay? So mathematically, that means for a transpose convolution based on a kernel U, the forward pass would be implemented in this way. I mean, would be mathematically equivalent to doing that, also including the reshaping. And that would produce a vector which is larger than the input Vx. Okay? And the backward pass would be implemented by just multiplying the loss by U instead of the transpose of the convolution matrix. So, graphically, this is what would happen. If we start from a small image, let's say a 2 by 2, which is you see at the center, you flatten it, that produces Vx. Then you define a regular convolution, let's say with a 3 by 3 kernel. You derive its convolution matrix U, but then you say, okay, you will multiply Vx by the transpose of this convolution. What you will obtain now is this much larger vector, in this case a 4 by 4, 16-dimensional vector, which you can reshape into a 4 by 4 image. Okay, and so effectively that means through this transpose convolution, we would go from a 2 by 2 to a 4 by 4 tensor. And this way we would have made the input larger than originally. Okay? And so the idea then is quite simple. If we go back to this, every time you need to upsample to increase the dimension, we just do that using one of these transpose convolutions. And if you do that, what you obtain is what we call a fully convolutional neural network. So it's a neural network in which you have only convolutions or only transpose convolutions. And typically you will have a bottleneck in the middle, and you can use that to do segmentation. Okay? Because an alternative to the two options you propose would just have been also to use regular fully connected layers, which you can use to increase also the dimension of the input. Okay? However, if you do that, then you are bound to some output dimension and some input dimension. What is a bit different with a fully convolutional neural network, and that's something a bit peculiar, but actually if you have a neural network in which you don't have any fully connected layer, you only have convolutions, nonlinear activations, or transpose convolutions, then the dimension of the input is not fixed. You can apply it to small and also to larger images. The same network without retraining. Okay? Okay, then we arrive to this. So this is actually the first instance of what we call the encoder-decoder paradigm in deep learning, in which we will have an architecture made of two parts. This first half, which we would call now the encoder, which is just responsible for processing the input, then processing and producing features that are relevant for the task that you want to solve after. And then finally, from these features, you decode them into, for example, a segmentation mask. And you do that through another neural network, which goes from something which is small and compact to something much larger, at least along the spatial dimensions. The issue with this architecture is that, okay, at least one of the big issues with this encoder-decoder architecture is that at every block of the encoder, you will compress the information, and you will remove, you will make the spatial dimension smaller. Which means that if you have then at the output to produce a very fine, high-resolution segmentation mask, you need to remember a lot of information in the middle to be able to reproduce this exact boundary between the classes. And that may be difficult to do, but you can try, and you will see that it will work, but you may not have the best results. Okay, so what we say is that at the middle, we'll have a bottleneck in terms of the information which is preserved. And if you compress too much, then this bottleneck will hurt your performance because you will not be able, from this very compact representation of the input, you will not be able to recover the very fine and exact boundary that you should produce at least for this task. So how do we go and solve this problem? You can do that with what we call the UNet architecture, which is, again, an encoder-decoder architecture, the same as before, but the main difference is that we add skip connections. So instead of just having one path going from the image, then down spatially, finally through the bottleneck, and then back up through the decoder, where at every step you increase the dimension. When you compute, for example, these first convolutions, you do that from the feature map that you have upscaled from the previous layers, but also you concatenate this upscale version with, for example, the feature map that you've produced at the corresponding layer, at the corresponding level in the encoder. Okay, so effectively here the information would have two paths. For example, this way, and also through the skip connection, like this. And this way you can, basically what will happen is that the network will learn to compress the relevant information in the middle, and basically usually like the semantic information or the high-level structure of the thing that you need to produce the output. And then all the high-frequency details will be just recovered from the skip connections. Okay? So it's as if you were computing, you were reducing the number of frequencies in the compression through the encoder, and when you have to rebuild an output of the corresponding size, you use both the high-level structure that you have produced just from the layers before, but also from the corresponding level in the encoder. Okay. Yeah, I think that's it. Other than that, you see that this architecture is almost like what we have seen last week. You just concatenate, you just stack convolution pooling, and you repeat that several times in blocks. Okay. And here for the decoder, it's almost the same, except that in between two dimensions, you have a transpose convolution, which will scale up the spatial dimension. But after the transpose convolution, then again you can have convolution ReLU, without the pooling, of course, because you don't want to decrease, you want to preserve. Yeah, one way to understand that is that you just take the same architecture as for the encoder, you swap everything, you mirror everything, you replace all the pooling with the transpose convolution or the upsampling that you have proposed, and then you do it first instead of last in the encoder. Okay? And what is also interesting to comment is the very last layer where you see conv one by one. What does that mean? What do you think? So if you see, for example, this one, conv 3 by 3, what does that mean?
The kernel is size 3 times 3.
Exact. Now, what if you have conv 1 by 1? Yeah.
What if I use the element, we multiply all the elements by the same value?
Mm-hmm. Why would we do that?
Because the data were normalized at the previous step to saturate the
No. So why do we have these one by one convolutions? So if this is the input, and then we do convolution with a kernel of size 1 by 1. What's the dimension of the output? 2?
I each times the volume.
Yes. And what about the number of channels?
Then we have one kernel, we have one channel.
Yeah, correct. So what do you think will be the effect of this operation? Yeah.
It will apply, it will take the vectors of probability and then...
Yeah, it's because actually this kernel is not 1 by 1, it's 1 by C. Right?
We quickly choose one class to cover the pixel width.
It choose one class.
Yeah, because the output is our method is segmented with each pixel covered a portion of its class.
Yes.
You have to pick what is the most probable.
Well, that we'll do later. For now, we are just producing. In this case, it's a binary mask, so we produce one output slice. But so basically, how should you interpret this operation? So when you do a 1 by 1 convolution, what you should understand is that you preserve the spatial dimensions. Okay, they are preserved. And if you just have one by one kernel, you are just basically computing a weighted average of the slices, of the channels. That's it. It's just a linear model. Okay? Because you will have C values there, some weights which will have to be learned, and effectively what you will do is that you multiply these pixels, this first pixel there with this one, then the second along the channel dimension with this one, and so on and so forth. And you will reuse the same weights for each of the pixels. Okay, so it's as if you were just taking a weighted average where the weights are defined by the kernel of the slices of this tensor. Okay? And so this one is also very convenient to use when you want to preserve the spatial dimension and just change the number of channels. If you say you have one kernel, one by one kernel, you will have one slice of dimension HW. But let's say if you want to map your abstract features and you have, I don't know, 32 of them, and you want to map that to your number of classes, you just have to do that as many times as you have classes. So you would use as many kernels as you have classes. Okay? Okay, so this architecture is actually very important. That's something we'll reuse much later in the course when you talk about deep generative models. So it's important that you understand it. You can generalize that to tensors of more than 2 dimensions, 2 spatial dimensions. This is an example, for example, on 3D segmentation on tissues. So in this case, you have slices of a tissue which have been acquired by a microscope, and you want to basically, in this case, find the task is to find the membranes between the cells. You can do that individually for each slice, or you can also have just a single unit but directly operating in 3D. And so you could generalize the convolutions also from 2D to 3D and solve the task all at once. You have questions on this? Okay. What I want to do next then is to implement this unit with you, just to show you that it's not that complicated, but still, if you have to do that for the first time, it can be a bit puzzling. So let me switch. Okay. Ah non. Ah, c'est bon. Let me just start the notebook. Okay. Okay, so, okay. Can you all read? Okay. Okay, so what I want to do for this demo is to take a data set of images, and I will want to solve one of these classification problems, and I will show you the images we'll work with. Maybe I can show you them. I can show you. So we have images like this, okay, which have been acquired by a microscope. And what we want to predict, given one of these images, is, for example, so this is 12. We want to predict the corresponding mask, where in black, or, I mean, depends on the color, you can inverse that. But in black, you want to find the membranes, and in white, everything else. Okay? And you can use that then to basically locate the cells in these tissues. Okay? So we can frame that as a segmentation problem, for which, given an image like this, we want to produce a binary mask of this kind. Okay? And so what we'll do is to try to implement this unit neural network to solve the task. Okay? You also see that these images, originally they are 500 by 500. Since I will use a unit, what I will do instead is to train this unit on small crops, in this case of size 100 by 128 by 128, and if indeed everything is fully convolutional, then I should be able to apply that later on to much larger images if I want. Okay? And why am I doing that? Because in this way, by just considering random crops, I will also increase artificially the size of my data set, because really to solve this task, I only have access to 30 images. That's not very large when it comes to deep learning, and still you will see that we are able to solve the task. So I just have there some code which is not very interesting, where I just open the two, so for each image, I have the actual image and the label file. I open them, I randomly crop them exactly in the same way. Then I convert everything to grayscale, and finally to tensor. And then I concatenate, I stack everything to produce my input dataset, which I standardize, and I do the same for the labels, okay, the Y values that I have to predict. And I just say that everything which is below 0.5 is of the positive class, and everything above is of the negative class. Okay, here I'm just producing a data set of 5,000 random crops. So that takes a few seconds. Should. Okay. And now if you look at this, okay, we have two tensors. The first one, the input, is made of 5,000 elements. And then the next dimensions are the number of channels. I have only one input channel, in this case because I've put everything to grayscale. And I have images of dimensions, spatial dimensions, 128 by 128. And for the mask, the labels that I want to produce, in the Y tensor, I have as many as I have for the inputs. I have only one channel because I have just a binary mask. But if I wanted instead to predict several classes, the second dimension would be larger than one, and I have the same spatial dimensions. Okay? Then, given this tensor, I define my data loader, which will produce random mini batches of size 32. And if I show you, let's say, one random image, you would have something like this. So this is not an image from the training set, this is a random crop from one of the images of the training set. Okay? So now given this image as input, we want to train a neural network which would be able to produce this as output. Okay? And this is another image. You see that there is some variation from one to the other. So it's not an easy task. And we'll see if the neural network is able to solve it. Okay? Okay, so the architecture that we'll implement will be a U-Net architecture. And so the idea is that we'll start from an image. So this represents the image. It's a 128 by 128 for the spatial dimensions. So in my drawing, in my diagram, the 8 of the rectangle will correspond to the spatial dimension, okay? And the width will correspond to the number of channels. So initially, we would have one channel. Okay? And the architectures that I propose to implement will first do a convolution. I will preserve the spatial dimension. Okay? So I can set some kernel size and define the padding accordingly to make sure I preserve this spatial dimension. Okay? So I will have, for example, the first convolution. And let's say I will be mapping that to 64 channels. And I preserve the spatial dimension. I will have a ReLU, which I don't show. And again, I will do another convolution followed by another ReLU. Okay, like what you would do typically in a regular CNN. You would have convolution, ReLU, convolution, ReLU. And then typically you would follow that by a pooling operation, which would reduce the spatial dimension, let's say by a factor of 2. So now the spatial dimension will be smaller by a factor of 2, but I would preserve the number of channels. So this would be 64 channels, and the spatial dimension now would be 64 by 64. Okay? So I would have a first block like this, and then the idea is that I will repeat this twice to have 3 blocks in my encoder. Okay? So this will be followed by now a convolution where I preserve the spatial dimension, but I increase the number of channels. So here the width is twice larger than this one. I would have now 128, and I've preserved the spatial dimension. Okay, so far? Then I repeat. I have a ReLU. I repeat this. I have another convolution, 128. And then, as in the first block, I would reduce the spatial dimension by a factor of 2. Okay, to obtain 128 channels and a spatial dimension of 32 by 32. Okay? Then I have the third block, where I start from the same spatial dimension. I increase the number of channels, let's say by a factor of 2. So now I would have 256, 32 by 32. And finally, the last downscaling operation, where we would still have 256 channels, but only 16 by 16 in spatial dimensions. Okay, just so these two would be convolution. So everything in red is a regular convolution. In yellow, you would have a pooling. Okay, so far? Now, we are at the level of the bottleneck. So we could either just do nothing and directly connect that to a decoder, or we could do a few operations if you wanted. So I will just say that I have a few more convolutions, convolution ReLU, where I maintain the spatial dimensions and I maintain the number of channels. So 256, 256, 16 by 16, 16 by 16, and these are just regular convolutions. Droite. Merde. Okay, so that's the end of the bottleneck, and then we have to consider the decoder, where the first operation in an encoder block would be an upscaling operation. So, for example, implemented by a transpose convolution. So we would have something like this. So we still have 200 by 56 channels, but the spatial dimensions, they are twice larger. Okay, and just to insist that these are not poolings anymore, they are transpose convolution. I will show them in green. And now we will have 32 by 32. Okay, when we go up, what we'll also do is to reduce progressively the number of channels. We'll increase the spatial dimensions, but we'll decrease the number of channels. So exactly in the opposite, in a way opposite to what we did in the encoder, for which we reduce the spatial dimension but increase the number of channels. Okay? So how do we reduce the number of channels? By just doing convolutions. Okay? So the next one will be a convolution, but where I say that I'm using fewer kernels, maybe 128, while preserving the spatial dimension. So 32 by 32, and I would have 128. Yes. I would follow that with a ReLU, and I could have another convolution, which preserve everything now, 32 by 32, and this would be regular convolutions. Okay, now next we have to increase by a factor of 2, more or less, the spatial dimensions. So it would be at 64 by 64, 128, and we would do that with, let's say, a transpose convolution. And we would reduce now the number of channels by doing a ReLU, a convolution, to go from 128 to 64, and we would have preserved the spatial dimension. Okay, and then finally, yeah, sorry, this one should have been a bit smaller. I should have matched this 8. And finally, we'll upscale once again the spatial dimensions to obtain 64 channels for a shape of 128 by 128. Okay. And what we have to do is to produce eventually a segmentation map of this shape. So the spatial dimensions are already correct, but we have to predict only one slice. So number of channels in the output should be 1. Okay, so what I will do is that I will follow that again by just convolution. Let's say I'm going slowly to 32. Sorry, in red. So that, yeah, that should be twice 32. Okay, and then finally, I will have now 32 by 128 tensor, which I will map to a 1 time 128 using a 1-by-1 convolution. Okay, and that will produce the final output. Okay, so that would be a regular encoder-decoder architecture made of a convolutional encoder and a transpose convolutional decoder. That could work, but if you try, then you will see that you will not get the best results. What we need to do next is to add these skip connections. Okay. So what I will do is, when I will implement this architecture, just before a pooling operation, I will keep track of the tensor there. Okay? And why? Because I will also feed it to this layer. Okay? So when I will compute this convolution, I will concatenate this tensor of size 32 by 32 and 256 channel with this one, which has the same shape. Okay, so effectively, it's as if after the concatenation, I would have a tensor of 512 channels. You just add the two together, and for each channel, you have 32 by 32 elements. Okay? So I would have a first skip connection like this. Then I would have another like this. And finally, I would have a last like this. Okay? Okay. Yes.
Yes, here on the scheme, why do we add the skip connection on a regular convolution for the first skip connection and not for the others?
Not for the others, what do you mean?
I mean that we go from green to red, and the other we go from red to green.
No, yeah, that's a mistake. Yeah, of course it should be. Sorry, thank you. It should be there. And there, it should be there. Okay. Okay, so the way I will implement it is to say, I will define a block as one of these things. It will be just a very simple neural network made of 4 operations: a convolution, a nonlinear activation, a convolution, and a nonlinear activation. And you see that if I define this, I will have also a block there, 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 and a block there. Okay? Then I will say that they have downsampling blocks, which are made of a block first and of a downscaling operation, in this case a pooling operation. So down will be block and then pooling. Okay, and I will have this downscaling block, I will have 3 of them. A first one here, a second one here, and a third one here. And finally, I will similarly define an upsampling neural network, which I will define as a transpose convolution first, followed by a block. Okay? So let's implement that. Unfortunately, I cannot put back the white screen there. Can you all read on this one? Maybe like this. Okay, so how do we implement a first block? Well, I will specify that as a neural network. Okay, so I will just have a block class which I define, which inherits from the neural network module, okay, in PyTorch. And when you implement an object which inherits from this neural network module, you have to specify the constructor and then how you implement the forward pass. That's it. So I will first define the constructor. Okay, where I can pass any arguments. In this case, the only thing that will change from one block to the other will be the number of input channels and the number of output channels. Okay, so I will just pass that as argument. Okay, and then I will say that a block, or maybe I should first call the parent constructor, and then I will say that a block, I will define a block attribute as a very small MLP, okay, which I will define as a sequential. So sequential is a construction that you can use in PyTorch just to chain sequentially layers. Okay, so in this case I would have first a convolutional layer, a 2D convolutional layer. So this is conv2D, and I have to pass a few arguments. So the first one is the number of input channels. The second one is the number of kernels you want to use in these convolutional layers, which in this case simply correspond to the number of output channels. Okay, the number of kernels or the number of output channels are just the same thing. I will also define the kernel size. Let's say I want to use kernels of size 3. And I will use a padding of 1, because when you combine that with a kernel size of 3, that will preserve the spatial dimensions of the input. Okay? That's my first convolution. Then I have to do a nonlinear activation function, so I could do ReLU, and I will repeat that with another convolution and another ReLU. I will follow that. Okay? Then I'm defining the forward pass, which will take X as input, and will return, well, the value returned by the block attribute. Okay? Okay, now I will define my two compositions, the down blocks and the up blocks. So I will do something very similar. I will say that I have a down class which inherits from the same neural network module. I will do something similar. Boom. And I said that I will define a down block by a block and a pooling. Okay, so I will have self block, which is a block, like an instance of this class, in channels, or channels. And I have a downsampling layer, let's call it down, which in this case would be, let's say, max pooling. Max pooling 2D, for example, with a compression factor of 2. Okay? Then I define similarly the forward pass. And what should I do? So how should I implement the forward pass? Can you tell me? Yeah. Yeah, you could do it like this. So what he says is to do self down of self block X. That would work. You could do it like this. Okay. Usually when we start chaining many of these layers in sequence, writing everything like this in one line can be a bit confusing. So we just write it as self block X, and then X is equal to self down X, and return X. But that's strictly equivalent. Okay? Okay, now the up class. Again, I will reuse this. And what do I need in this? I need a transpose convolution and a block. So I will say that up is equal to an in PyTorch you have a transpose convolution, transpose 2D, where you have the number of channels as input, the number of output channels. Let's write it like this. Kernel size equal to and stride of 2. Okay, and that will result in the spatial dimensions being increased by a factor of 2. Okay? Then we have the block. And what should be the dimension? Or the arguments? Yeah. Now, I made a mistake there. Can you spot it? At least it's not consistent with the diagrams. Yeah.
It's in the convolution transpose,
The in channels is correct. I mean, this one is correct. No, it's the out channels. So because I said there, I would preserve the number of channels. You see, 256 remains 256. So I should keep it there. So the number of outputs of the transpose convolution is the number of inputs in this case. Okay, and it's only at the block where I will adjust the number of channels. Okay, and you see that actually I made a mistake there too. In the sequential of the block, I first change the number of channels, and then I keep working with the same number of channels. Okay? All right. Self X. Alors, what should I do there? I said I would first upsample by doing the transpose convolution, and then I would do a regular block. So I could just do X equal self up at X, and then X that you pass to the block, right? And then you return X. Okay? Yes? No, because, yeah, correct. Thank you. Anything else incorrect or missing? Okay, merci. Well, actually, I'm missing the skip connections. So to introduce the skip connections, I would need, let's take this one, in this, for example, in this down block. So the output of the down block would be this tensor, but I would need to concatenate later on with this tensor. Okay, so I should keep track of this one. So that's what I will do, and I will return the two of them together. So what I need is to keep track of this output, the output of the block, because I will pass it down through the skip connection. Let's say X down. Let's do it like this. Okay. And now I return the 2. Okay. Now, how do I reuse that? I need in the upsampling block to change the forward to accept 2 inputs. Okay. So this up block will take 2 inputs, this one and this one. Let's call it skip, like this. So X is, so this X there is what is coming from the bottleneck in the previous denoiser block. Okay, so this is fine. And the skip connection is what arrives from the denoiser. But when I do the upsampling, I'm only upsampling the information from below, so it's only on X. And then, when I have the block there, I need to apply this block on the concatenation of this and the content of the skip connection. Okay, so I will say that X now is the concatenation, which you can do with cat of X and skip, except that these guys, they are 4-dimensional tensors of batch-sized channels width and 8, so you need to specify along which dimension you concatenate. In this case, it's on the channel dimension, which will be my second dimension. Okay? So at position 1. Okay? And now we should have everything to implement our tiny unit. So, up. So what do we need? Again, we need to know number of channels. So how many we have as input, how many we want as output. Like this. And now it will be quite easy. So what should I do? In the constructor. So in the constructor, I need to instantiate all these blocks. That's it. So I will have 3 down blocks, 1, 2, 3. I will have 3 up blocks, 1, 2, and 3. I will have this middle part, which I will implement as a block. And I will have the final one-by-one convolution, which you don't see. Okay, so let's do that. So I will have the first implemented as a down block, where the number of input channels is in channels, and the number of output channels will be 64. Then I have the second one, where the number of input channels of the second block is no. No, the number of inputs. The number of inputs should be the number of outputs of the previous block. So 64. On the other hand, now we want to increase the number of channels, so we can double it. And finally, we will have down 3, where the number of inputs will be the number of outputs of the previous one, and we'll have 256. Then we have the bottleneck, which I will implement as a block, where I preserve so this is a block where I preserve the number of channels. So I will say that I have 256, and I map that to 256 other channels. And finally, we'll have the up. So we'll do it in the opposite way. Okay, there is a mistake. Okay, so I'm mapping that from 256 to 128, self to up 128 to 64, and then the last one, up 64 to 32. Okay? And finally, I have the last convolution, the one-by-one convolution, which I will implement as a conv2d directly, where I have 32 inputs, and the number of outputs is the number of channels, this one. And to say I want one-by-one convolution, I'm just saying I have kernel size equal 1. Forward. Okay, now how do I implement the forward pass of this? So a good habit that you should take when these things will become more complicated, and that's very useful, is to, at least that's something I do, is to keep track of the shape of the tensors along the forward pass. And so in this case, the shape is of X would be a tensor of size B, the number of elements in the mini batch, of size where we would have as many channels as we have in channels, and we would have initially 128 by 128, so H times W. Okay? And then the first thing we should do is to pass this X to the first down block. Okay? So let's do that. X down of X. Okay? But this wouldn't work because now the down operation produces two values. Okay? So we'll just keep track of the two. So I will have x1 and x, which I will keep passing down. Then x2 and x, they pass to the up. It's not like this. Self down 1. Self down 2. And finally x3, x, self down 3. Okay? Where x1, x2, x3 are the values that will pass through the skip connections, and the x at this position correspond to what will enter inside the middle block. So now I say that it's equal to this. And finally, now I need to go up through the architecture, through the decoder, and I will do that by saying that x, I will call it on the first up block, up 3, where I pass x and x3. Then I have the same up 2, where I pass x and x2, and x, I pass up 1, x and x1. Okay, and finally I have the last convolution, and I return x. Okay. And if we reason about the dimensions, we have after the down 1, x1 has the same spatial dimensions, so we would have, for example, that x1 is b, but 64. We've mapped that to 64 channels, and we have preserved the spatial dimension, hw. On the other hand, for x, it has passed through the pooling layer, and x is the same shape for the two first dimensions, but twice smaller spatially. Okay, and you can do the rest, and everything should be okay. Okay, so let's see if that works. So I will instantiate this network, tiny unit. I will say I have inputs with one channel and I want outputs with one channel. I will put that to the device. And I will evaluate that, let's say first, on the first element of the dataset. And I will get an error. Okay. Okay, so what's going on? It says that the shapes are not compatible. Why is that? So you see, it expected it expected 256 channels, but it received 500 of them. And this happens if we go up just after the concatenation. So in the block of the upsampling component. And the reason is because when we have implemented this, we've made another error. We have said that the number of input of that block is the number of input channels, but that's wrong because we have concatenated in channels, we have concatenated X with the skip connections. Okay, so we are doubling actually the number of input channels. So if we say twice the number of channels, that should work. Okay, now remains to train this thing. Okay, so what do we need when we have to train a neural network? We have the architecture, we have the data, what else? We need 2 more ingredients. Sorry? No, the MLP would be the architecture. In this case, we will have this tiny unit. So the architecture is, we have it, yes. So the weights, you mean?
To track the training error to be able to plot.
Okay, yeah. But by the way, what error are you talking about? We've not defined it. So we need a criterion, we need a loss. What could be the loss in this case?
The cross entropy.
Mm-hmm. Yeah, and why the cross entropy?
Because we have classification.
Yeah, because this segmentation, at least for binary mask, is just classifying each pixel. So we can use then a classification loss for that. That's what we'll do. So I will use the BC with logits. So I'm using this one specifically because if you paid attention, after the last layer, I'm not passing that to a sigmoid activation function. So they are not probability estimates. Okay? But if you use this binary cross entropy with logit loss, what this loss expect as inputs are the so-called logits, so what you get before the sigmoid, and the function itself will do as if there was a sigmoid after that. Okay? What else do we need? Okay. Which one would you use? Yeah, okay. So I will use Adam. And I need to specify the parameters I want to tune. So in this case, they would be given by the parameters associated to this object. Okay, and then I will repeat my training loop 5 times, let's say. So I will iterate 5 times over the training set. And I would iterate by mini batches, which are given by the data loader, which I've defined just there. Okay. Then I transfer these 2 guys to the GPU. Okay. And what do I need to do next? I need to compute the predictions. How do I compute the predictions? By doing a forward pass through the network. So I'm just calling the network on the input that produces the outputs. And then I can compare these predictions to the ground truth, y, and I can do that through the loss. Okay, so the loss is the criterion which I evaluate at y pred and y. Okay. Then I reset the gradient. 0 grade. I compute the gradients. And then I do a step. Like this. And I will print the value of the loss at every update. Okay, should work. We'll see. Questions meanwhile? So it will run for 25,000 updates. It will take a minute or two. Okay, so while it's training, so I really wanted to do that slowly, just to give you the idea that when you have a very big neural network to implement, it becomes super easy to implement if you decompose that into smaller blocks, okay, which you implement by themselves, and then you just compose these blocks together to arrive to the final network. Okay, and we'll see 2 weeks from now when we actually implement the transformer network that will just follow the same kind of design. We'll just define blocks one by one, and then we'll compose them into bigger and bigger architectures. Okay, so it's trained, the loss has decreased. Let's see if that works well. So I will take a random mini batch. Like this. Then I compute the prediction by just doing a forward pass to the network. So now what I have there is a tensor of size 32 by 1 by the shape. But these are the logit values. Okay, if you look at the first element, you see that you have values of -2, -4, 0. So these are not probability values. Okay, I can make them probability values by saying that I pass that to the sigmoid activation function. Okay. And now all these numbers, they are positive, and they are positive, and each of them is smaller than 1, so they are regular probability values. And now I will just show you the mask which is produced. So if we look, for example, at x0, then like this. I have to pass that to NumPy. Okay, so this would be the first image. And the predictions would be, so that would be a different image now, but whatever. Ah. Qu'est-ce qu'il veut? Okay. And these are the masks produced by the neural network. And you see that that seems to work quite well. Questions? So the full example and the entire code is on the GitHub if you want to have a closer look. But you see, in just 1 hour, we implemented a unit and we solved the classification task, the segmentation task. Okay. Yeah. So this unit architecture is quite important. Basically, you find it almost everywhere in modern neural networks. It's something that you can use to solve many other tasks than segmentation. Later on, when we talk about diffusion, you will see that at the core of the diffusion model, we'll have a neural network, which we can also implement as a unit. So same network, it's just the output, which is a bit different. But other than that, it's just a regular unit. Yeah, and then finally, but this is just for your own information, there was these 2 last slides about mask RCNN, which is how to implement panoptic segmentation, or how to implement instance segmentation. Well, you can take, let's look at this one. You can take one of these neural network which is able to do object detection, and you add another head. So for example, if you have one of these two stages neural network, you would have first, for each proposal, you would have a prediction for the category, the bounding box, but you can also couple that with a neural network which does segmentation on the corresponding region. And if you do that, you have two neural networks that are able to do things like this, to both detect and segment with the same architecture. And you can also watch this. So that works very well, and this was the state of the art for a few years, but I think last year or 2 years ago, now we are using quite different architecture to solve the same task. The state of the art now is by a network which is called Segment Anything by Meta. Because one of the issues with these neural networks that we've seen is that we have to predefine the classes. We have to say in advance, we want to detect cats, dogs, but then if you train your neural networks and eventually you want to detect giraffes or other things, you can't do that. Okay? With the new generation of neural networks, you can do that. You can specify at test time the kind of things you want to detect by just specifying that with text, okay, and this text would be mapped to some content, or rather the image of the content of the image would be mapped to the same position, to the same kind of vectors than the text, and everything which would be aligned would be detected. Okay, so for example, you can say cat and it will detect all the cats. Okay, but this is quite different from what you have seen. But if you're interested, it's called Segment Anything. This is the version 1 and there is the version 2 already. Okay. Yeah, that's it. Questions? No? Okay, thank you.